Okay, this is Derwin King with Sampson Community College. This is hydraulics and pneumatics class HYD-110. Anyone that could not make it today, Brandon, particularly for you, hope you're doing okay. This is January 14th. We're going to pick up from where we left off in our book and keep rolling. Okay, so we're going to look at something called Pascal's law. And what Pascal's law says, and he was one of these early, guys that defines what we know today. You put it in words. It says that when a gas is confined under pressure, whether it's air or some other type gas like it could be argon, helium, or something like used in the welding shop, but gases in general, that the pressure within that vessel, it'll be transmitted equally in all directions. That's Pascal's law. Most tanks are going to be shaped like that. They're going to be oblong with rounded ends, and it's a design that lets them do it with thinner material and still be able to handle the pressure. And the next thing about our theory here would be that the relationship between pressure of the gas and the volume is given in another law called Boyle's law. So this is something that, in your worksheet in Moodle, there's questions all through there to deal with, Pascal's law, Boyle's law, there's Charles' law. Once we get past this chapter, it's just going to be more practical. It'll be a lot of hands-on, but this is the underlying stuff that we understand how it ticks, which is important. It's important when you troubleshoot, when you get unusual problems with fluid power, to know really the nuts and bolts of it. So Boyle's law says the absolute pressure confined quantity of gas, it varies inversely or oppositely with volume, as long as the temperature does not change. So basically, if you increase the size of a tank, then the pressure would go down. You know what I mean? If the same amount of gas was in there, and you increase the size of it, the pressure in it's going to go down. It's going to be opposite. But if you decrease the size of the vessel, then the pressure is going to do what? You have to go up, and that's what we get into when we're talking about an air compressor. Well, the air compressor, they have an intake stroke where they pull air in from the atmosphere. They pull it in, and then when they compress, they're changing the volume, the area of the inside of the piston where they're compressing the air. And so when you squeeze that air, what happens to the pressure? It goes up. When the size, the area of the inside of the compressor changes, when the piston compresses it, that pressure is going to go up. That's how a reciprocating compressor does it, is by compacting that air. It traps it, it brings it in through the intake valve, and then a check valve shuts. So on the intake stroke, a check valve opens up and it pulls in X amount of air into a chamber, and then the check valve slams. And then it compresses on your compression stroke. And when it gets up to a certain pressure, a discharged check valve pops open under pressure. And it discharges it out of that chamber at an increased pressure. And then it does another suction and another compression stroke. So that's how a reciprocating compressor does. The one above our head in here, you hear how loud it is, the air compressor, when it comes on, and it goes tuk-tuk like that, super loud. That's how it does it. It does a real fast reciprocating motion. So it's doing what we're saying here. And they're saying if you got 10 cubic feet of air, which means 10 by 10 by 10, a cubicle. A cubicle is 10 by 10 by 10, or 10 cubic feet. At 14.7 psi is compressed down to 1 cubic foot. The air pressure is going to go up 10 times, so 147 PSI A are absolute as long as the air temperature remains the same. But in reality, when you compress it, now it's going to get hotter. You're going to find out it does get hotter. They're saying on paper, if it didn't get hotter, if you just decrease the size of it and the temperature don't change, but at the same time, it's going to get hotter. And when it does, it's going to go up even more. So it's going to go up even more than that because of the heat. When temperature goes up, like in your tires on your truck and your car, what happens in the summertime compared to the wintertime? You know, the air pressure can go up compared to, say, let's say this morning, if it's 32 degrees outside, and if you got a display that shows air pressure on your vehicle, how many of you shows your dad shows your pressure? So in the morning, you might be reading 30 pounds, but when you take it up and down the road, what does it show? 32, 33, right? So as it gets hot, just the heat itself makes the pressure go up in the tire. And so that's where the next law is going to show you about temperature. You know, so okay. So your first equation is this: that if you got a container there, pressure one would be the beginning pressure of that container in the beginning. If you take that pressure times the volume in cubic feet or inches, whatever that equals, it would be equal to the pressure times the volume when you change the volume. So in other words, if you increase or decrease the volume, in the second scenario of that container, the pressure 2 and the volume 2, when you equal that, when you multiply that, technically they will equal. They will equal, you know. And the reason why it does is because, let's say if you go down on the volume, and V2 is smaller than V1 on volume, T2 goes up in the same exact proportion. So whatever, if it goes, let's say if the volume goes down 10%, the pressure is going to go up 10%. So the product of those two numbers, when you multiply them, the product is going to be the same thing. Does that make sense? Because one of them goes down, the other one goes up in the exact proportion. So the answer to that multiplication problem will be the same as it was over here. The final answer will be the same. So you'll need this on solving some of your problems in your worksheet. The volumes before and after compression. We're talking about air compressor here. You can also say that pressure 2 divided by pressure 1, whatever that ratio is, would be equal to volume 1 divided by volume 2. So they got pressure 2 over pressure 1, and then since pressure and volume are opposite, or they're inversely proportional, when one changes, the other one goes the other way. They flipped it over here on volume. They said that P2 over P1 equals V1 over V2. It's opposite because the relationship is opposite. And to allow for the effects of atmospheric pressure, this is important. This is something that you have to remember when you're doing calculations right here. So make a note in your book. To allow for the effects of atmospheric pressure, always remember to convert gauge pressure before solving the problem, and then convert back to gauge pressure after solving it. What do we mean by that? Is if you have a problem and it involves some pressure, like say 80 pounds, 80 psi G, get gauge pressure. They'll give you some number in gauge pressure, And then they're going to give you some scenario. You're going to do a calculation. Well, before you do the calculation, you got to convert the gauge pressure over the absolute pressure by adding 14.7 to it. So if you add 14.7 to that, what do you end up with? 94.7. That's the number that you're going to do the calculation with. When your calculation is finished, then you're going to go in reverse order and take that final number after it's changed, and you're going to subtract the 14.7 and go right back to gauge pressure.
All right, so now you said that 14.7 is just like atmospheric pressure and all that.
It's sea level.
Okay, so if you change the elevation, you have to change that number?
If you were going to be exact, yes. If you were going to be exact, yes, sir. If you were on Mount Mitchell, it would be different. If you were, say, at the Dead Sea, where they say, it's below sea level over in Middle East, it would be different. But your calculations are going to be based on sea level.
Okay.
They don't get so detailed in the book that where they're going to tell you where you are. They're going to assume everything's going to be at sea level, because unless you're in a mountainous area, it's not going to be that a whole lot different from sea level anyway. So, yeah, if it ever mattered, they would tell us. It's for true engineers that work, say, Colorado, that got industry up in the mountains and high areas. I'm sure they do that. I'm sure they take all that into account. Or engineers that are over, say, in the Middle East that are in those low areas below sea level, if they got an industry, they're probably doing that. They're probably taking all that into account, But this is one that if you don't do this, the answer is going to be wrong on your calculations in the worksheet. So that's a really important one there to remember. Okay. So you'll add the 14.7, do whatever calculating you do, and then you're going to subtract it back out. Usually a compression problem like the one above is stated as follows. What is the gauge pressure of 10 cubic feet of air at 25.3 psi G gauge pressure when it's compressed to 5 cubic feet, which would be, compressing it in half. Okay, so here's the steps that they go through. And again, you just kind of bear with me through chapter 1. After that, you don't have all this stuff to deal with. You only have one chapter calculations. That's it, the best of my remembrance. I've taught this a couple times before. I don't remember no calculations beyond chapter 1, so not bad to know it anyway. So you're going to start out by converting the 25.3 over to absolute pressure. Now, we'll say this for any of you that are going to be taking refrigeration classes, or if you ever get into ammonia refrigeration, in the refrigeration world, you do have to do what we're talking about here. You have got to convert things over to absolute to do calculations. It's a normal part of refrigeration. Anybody in here, is anybody not had refrigeration class that's going to take it to get your degree? So this gets you ready for refrigeration. It does. It actually in refrigeration, they've actually got some gauges. I asked Fran about it. I said, do y'all have gauges that read that? He said there are some gauges that actually read that, but he doesn't have any of them down there. But when they do calculations, they actually use this. I've taken 2 refrigeration classes for ammonia myself in Georgia, and it was loaded with this stuff. It was loaded with it, it really was. So you're taking the original 25.3, you're adding 14.7 to it, which gives you 40 psi of absolute pressure, and that's counting the atmospheric pressure of the gases that surround the earth and all. It puts pressure on us. See, if you go to the moon, there ain't no atmospheric pressure. There's not. on the moon. You can Google it. There's not enough to even, it doesn't even amount to anything to even hardly measure. But here, because of the layers, there's layers of gases that, and that it produces pressure on us. So you take the 40 PSI there, and if you're going to calculate the final pressure, the equation would be that P2, your final pressure, would be P1, pressure 1, times the ratio of volume 1 divided by volume 2. And if you take the absolute pressure and then you put it in there with volume 1 is 10 cubic feet and volume 2 is 5 cubic feet, and you multiply that out, it would be 40 times 2 would be 80 PSIA, absolute. And so are we done? Are we done with the equation or not? Or do we do something else? You've got to go back from absolute back to gauge pressure by doing what? You got to minus out to 14.7, yeah, to get you back to gauge pressure. And what that does is it nulls out the pressure in the air. It's like it's recalibrating your gauge to subtract that part to give you the actual what a regular gauge would read. You know. Yeah. I'll have to get, well, actually, anytime that you go by, whenever you go by these trainers out here, look at any of the air gauges because none of them are hooked up. They're open. They're just open to the room right now. There's no hose in them, and you'll see they'll read 0. Unless they're out of calibration, they're going to read 0 to room pressure because they're actually calibrated to subtract this. So you take the 80 minus that, and it ends up being 65.3. Looks kind of odd, don't it? But that's the way it works. And so that formula there came from if you're solving for P2, if you're solving for P2, so for this formula right here, if you want to get P2 by itself, if you multiply both sides by the same thing, let's just draw it up here before there's some more room. Right there, just say P2. P2 over P1 would equal V1 over V2. If you're solving for P2 and you want to get it by itself, if you multiply both sides of the equation by P1, it's going to cancel out P1 over here, right? And it'll end up being that P2 equals V1 over V2 times P1. So that's how they come up with that. So this is what they put out for you. And I like to try to slow down and say, well, how did they get to where they are, you know? So. Good to go. Okay. So you'll see. It's the same thing. It's P1 times that. That's how they got to where they are there. I didn't mean to do that. But this thing, boys, something else. You got to be careful what you do. Eraser. This thing about drives you crazy sometimes trying to figure out what. Okay, so that was that problem. Your pressures ought to always be calculated based on absolute pressures instead of gauge pressures, or you get an incorrect answer. The next one will be Charles's law. This is one that's about temperature. It's about your car tire, what it does, free, cold versus hot. So you see this all the time in the winter. Charles's law says that if the volume of a quantity of gas remains the same as the volume size, if you change, then the change in the pressure varies directly with a change in temperature. So temperature goes up, pressure does what? Yeah, they're direct. They're direct. If temperature goes down, so it's a direct relationship instead of an inverse, like with volume. You know, volume and pressure are inverse, and you know, temperature and pressure are directly. And so you can calculate that by saying that the final pressure in a car tire or truck tire, P2, the final, would be the initial pressure in the morning times the final temperature divided by the initial temperature. You know, it could be, you know, if it's, you know, 80 degrees divided by 32 degrees, you know, as far as, you know, a temperature change. The ratio of final temperature over initial temperature, that ratio times your first pressure is the easy way to look at it. It's going to be a ratio or a percent. And Charles's law also says that if the pressure of the confined quantity of the gas remains the same, if the pressure remains the same, the PSI, but the volume changes. A change in the volume of the gas varies directly with a change in temperature. Let me back out and read this again. If the pressure stays the same, like 100 PSI, if you change the volume, then the temperature and the volume are directly related. Which means this, that the final volume, V2, would be equal to the initial volume times the ratio of your second temperature divided by the first temperature. So you might start out at, you know, your final temperature, T2 might be 80 degrees and the first one might be 32. So it's going to be some number above 1, right? And then that number, that factor will be times your first volume. And the final volume will go up. Now that could go up, say, for a balloon, okay? A flexible thing that actually can go up in size. So we're talking for something like, you know, let's be real, a car tire, you know, let's say, but that's not realistic for a car tire because, you know, the pressure changes. We're saying that if the pressure remained the same, but the temperature went up, then they're saying that the vessel would get bigger.
So what about the things that be blowing up in the sky? Don't they take like heat to blow the things?
Mm-hmm. Yeah, it's hot air. It's hot air that blows them up. It is. It makes them go up. Yeah. Mm-hmm. Yeah. Yep. 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 So that could be like related to, you know, a balloon, for instance. In both of the equations, your temperature is stated as absolute temperature. So here's something that it may be totally new to you, and you won't see it again in this book that I'm aware of. You're only going to see it one time. It's something called absolute zero. It's a temperature system called Rankine, and it's very rarely mentioned in maintenance. And I guess if you get in refrigeration pretty deep, they probably, I think it was brought up in refrigeration classes. Had some a few years ago. Absolute temperature is used when applying Charles's law to avoid confusion that might occur with degrees Fahrenheit or Celsius. So absolute temperature starts at absolute zero, which is actually minus 450 degrees, or 0 degrees Rankine. And you won't see it again in this book that I'm aware of. It's only one time you're going to see it in here. Rankine is the scientist who discovered absolute zero. You could Google, and I'm not sure how many years ago that was, but that fellow discovered it, and it was actually minus 450 degrees Fahrenheit that somebody discovered that. I don't know why he did that, what made him do it, but he did. So on that basis, 0 degree Fahrenheit equals a positive 460 Rankine, and 40 degree Fahrenheit equals the 60 plus the 460 would be, you know, 420, 420. But it's based on that absolute zero is minus 460 Fahrenheit, which is 0 Rankine, and then our 0 Fahrenheit would be a plus 460 Rankine. And then you got to add 460 to anything we have in the Fahrenheit system to give you the absolute temperature. You just add 460 to anything we have, and it's going to give you the absolute temperature. Don't get worried about this, because again, we ain't going to be we're not camping out on this stuff. We're going to do just what it takes to get you through the theory end of it. We're going to keep trucking. Because air cannot be compressed without the temperature changing. That's a fact. When you compress it, it's going to get hotter. It guaranteed to get hotter. They have something, matter of fact, up here on this compressor, as soon as it leaves the compression stages, actually between them, there's an intercooler between the two compression stages up here on this compressor. If you ever notice that, you'll see two things that are shooting out like that with fins on them, and there'll be a pipeline that goes between the compression stages with fins, with aluminum fins on there that cools. So after it compresses in one stage, it goes through an intercooler that cools the air before it even gets compressed that second time, because it will be too hot for that second compression stage, and they actually cool it between stages on a basic compressor like that up there. Or next time you see one in a shop, take a look at it, and you're probably going to see what I'm saying. You're probably going to see that cooler between those stages, because it gets so hot in that first stage that they have to cool it. And then when it leaves here, it's going to cool some natural through the pipelines. If you get in the plant with really big ones, they have after coolers that are either built into the unit or either right after it on the main header line coming off the compressor. It's got to go through an after cooler. It will be too hot before, when it got to the machinery. This is extremely hot coming right out of the compression chamber. It says that Boyle's law and Charles's law, they operate together according to the ideal gas law. So the ideal gas law tells you, it puts it all together, and it says the initial pressure times the initial volume divided by initial temperature would equal the final of all of that, you know. But you're talking about an ideal law that does take into account the reality of some, you know, a little bit of losses in things that happens in real life. Note this equation, it uses absolute temperature, PSIA, and absolute temperature in the calculations. But in actual practice, factors like humidity and the heat of friction and efficiency losses affects all gases, but they still use the ideal gas law for equations. They still use it for calculating. So now we look at, we start looking at cylinders and compression stages in a compressor. Using compressed air to do work requires the application of all these points. If you have a force of 10 pounds that's applied to a piston and it's transmitted through the cylinder to piston 2, Pascal's law says that pressure developed in a confined gas is equal at every point touched by that gas. Therefore, the internal pressure developed by piston 1 pushes on piston 2. If each piston area is the same, then the force developed on piston 2 will be equal to the force applied to piston 1 if you don't count frictional losses. This cylinder in A has been replaced by 2 individual cylinders in the B with a hose between them, with an airline between them. Both of them had the same diameter, but they're connected by an airline. And the conditions have not changed because the pneumatic system has not changed. The force would still equal here what's applied to that one. Primarily because your piston sizes are the same. The piston sizes are the same. This is where it gets different. So watch really closely right here. This is where things change. You get into something called pneumatic leverage, to where a small amount of pressure can do a whole lot of work. And this is to where designers use this to be able to easily do something massive with apparently a small power source that they can do, like a log split or something like that. You know, you get leverage to do work when you apply this. Unequal piston areas. Here they're saying that if you take and you set a 100-pound dead weight on that piston rod, we're talking 100 pounds of actual physical weight. If you set it on that rod there and it pushes onto there, and within the vessel here, it develops 10 psi. So how do we calculate that? Let's get out our triangle that we looked at the other day. And who can tell me our triangle with the 3 letters in it, what it was?
Area.
Right, FPA. Right. You got pounds, PSI, and then you have inches squared, right? So you've got pounds, and then you've got PSI, which is pounds per square inch, and then you've got inches squared in there. It'll help you a lot if you draw that triangle on all your calculations, and you'll sail right through this stuff. You'll knock it out. It won't be no problem whatsoever. So if we're going to solve for this and figure out how they got the internal pressure in there in this stage here, we know that we have 100 pounds, which would be F, and we got 10 square inches on the piston. Okay, so how do we calculate the PSI? We divide the pounds divided by the area, right? Mm-hmm. So it's 100 pounds of dead weight divided by 10 square inches, which equals what? What you're putting 100 pounds up here, right? In the equation, 10, it would equal 10 psi. If we cover this up, it's going to be 100 pounds divided by 10 inches squared. And so the PSI that's actually inside that container would be 10 PSI, 10 pounds per square inch. Now, when you get over on this end of it, it's where the leverage comes in. You know what leverage is. Let's say, for instance, that you want to, let's say, Costa, that you want to scoot the machine over the plant. You get you a piece of metal rod, right, and you get you a block set on the floor, and you get over here way out here at the end of this rod, and you have leverage, right? And you can move the machine you could never move on your own just by pushing. So this is that's mechanical leverage, and here you got pneumatic leverage. Now tell me, when you pivot with that long cheater bar and you move that machine, if you move a foot over here, the machine doesn't move so much over here, does it? The distance, but yet you got great power over it. You don't move it a lot. So when the advantage that you have, the distance you move over here, it's decreased over there, but the power is increased the opposite amount. Your distance and then your leverage are opposite when you get mechanical advantage. So the 10 PSI, but because what law says that if it's 10 PSI over here, it's 10 PSI over there? Whose law said that? Was that Charles or Boyle's, or was it Pascal? Yeah, this is a little when you have those laws. Hmm?
I didn't want to guess it and get it right.
Well, you can just look in your book. You got your book, yeah. Look, glance back at your book, yeah.
What is that, Pascal?
Mm-hmm.
Yeah, Pascal's law.
Right. So if you got a vessel, it doesn't matter what the vessel's shaped like. It can be oblong. It can be, it can be like a U shape. If it's enclosed and there's no leaks in there, and you pressurize it, it'll be equal forces in all directions within that vessel. So it says that if it's 10 PSI over here, then it will be over there too. That is if the fluid is actually under static pressure. You know what I mean? If it's not leaking, if it's not moving, you know what I mean? If it's not being escaped out of there. So based on this, how do we calculate the output force of this piston right here? So here I want to know, the question mark would be, I want to know the force output of the cylinder. So how do I calculate F? Yes, exactly. Look, if you take here, we're gonna cover up F. That's the output force of this, which is the unknown. And we know the size of the piston went up to what? To 50 square inches. It went up times 5. So it's 5 times bigger than this one. And so we know the area, and then we know the internal pressure pushing the piston. So you can calculate the output force, or you can calculate how much weight can the cylinder lift. If it was a bottle jack, say for instance a bottle jack, how much weight could that bottle jack lift? Under these conditions. That's a good example of you pumping a bottle jack. You know what I mean? How much weight could it lift based on diameter? A bottle jack. A little jack that you jack a car up with, a little hydraulic jack. I mean, that's a good example of something like this, that if you knew what pressure was going to be pushing that jack and the diameter of the piston, you can calculate the amount of weight it could lift. That's why that on those jacks like that, there'll be a maximum weight lift stated on that jack. That they got it on there, stamped on it. Yeah, they do. They got it on there. I mean, they calculated it using this. That's how they design them, and they tell you, it can't lift no more than so many pounds, of a vehicle or whatever. So,
what about like an elevator or something like that? Like the elevator, they got so like so many pounds you can put on the elevator.
Yes.
Something like that. Would that be? Would they use that to calculate?
Well, with the elevator, you're going to be using horsepower calculation. Yes. Okay. Yeah, you will. You'll be using the weight. You'll be using the distance. All that comes into play for an elevator. Yeah, yeah. We covered the elevator thing in intro to electricity. We got a formula for that. Yeah, we sure do. Yeah, you'll get that one. I can show it to you sometime, like in between class, and you'll use it in the fall.
Yeah, so I'm taking that class too. So that'll be.
You will in the fall. It's the very basic electrical class that you get in the fall. So you would normally start in the fall instead of starting now, but they let you start whenever you want to, so you can get on in and start rolling. So yeah. Okay. So we're taking the 10 psi, put it in where P is, and then the 50 square inches goes into here, right? So it's going to be the 10 times the 50. And so what's our output force?
10 times 50.
Mm-hmm.
50, ain't it? 50. Maybe 50, ain't it?
No. Look, you got 10 psi.
Oh, 10.
10 psi times 50 square inches, right?
Mm-hmm.
Well, you multiply. What's 10 times 50? 500, yeah. So it would lift a 500-pound weight. So here's the mechanical advantage. Is you took a 100-pound dead weight and sit on top of that piston. And then on the other end of it, it actually could lift 500. It sounds like magic, but it ain't. It's real. Now, who can tell me what does it cost and where's the payoff for you to be able to get 100 pounds and lift 500? You pay somewhere, right? So what do you lose when you gain that kind of advantage on lifting weight? Where does the trade-off come? Well, there's, the amount of work in terms of what? In terms of what measurement do you say that we lose when we gain to be able to lift that much more? What do we lose in a measurable thing? No, not pressure. You're actually gaining. I mean, you're gaining. The pressure's the same in there, but the output force. What do you lose? No. Mm-mm. Let me give you a little hint here. If I push that piston, if I pushed it 5 inches down, how far is that one going to move? Right. Huh?
About 2 inches.
It's going to be less, but your distance is going to be less. When you get that kind of mechanical advantage, if you move, say, 5 inches over here, the amount it moves over there goes down in the same proportion as your leverage went up. So the distance is what you lose. You've actually got to stroke further to get it to move however far you want to. It's the stroke length that you lose. That makes sense? It's the travel distance that you lose. It's because of the volume over here versus the volume over here. The surface area, your travel is what's going to be. It's the same thing like if you're trying to leverage a machine and you move it a lot over here with a cheater bar over there, it moves a little bit when you move a lot over here, right? If your block is sitting near the machine, it's the same thing. It's your travel length is what changes, what goes down. If you're getting ready to get into that now, there's actually a way to calculate that. But is everybody okay as far as how you got basically what we're saying here is that you could lift a 500-pound weight. This cylinder would lift 500 pounds when you put a 100-pound weight on the other one. If you just got a dead weight over here of 100 pounds, it could actually move 500. So that's part of your engineering. I think the things that they use, in plants when they design equipment, that's something that they all think about that whenever they're designing equipment. That's part of what goes into automating things that are very powerful, you know. I keep saying a log splitter, you know, things like that that do a crazy amount of power in a small package. That's what they're doing. They got some type of an advantage, major advantage, you know, that they're doing. Everybody okay with it? How do you like the triangle makes it clear, don't it? You got to have the triangle. If you don't, it's just, you know, you get foggy headed. I mean, I do. And I don't use this stuff very often, and you know, you just need to have it. You know, use those learning aids as much as you need to. So they calculate the stroke difference by using volume. The volume change, the actual exact volume is how they calculate that part. So they do it like this. There's another principle in leverage that must be accounted for, and that is for every force increase, there is a corresponding movement decrease. A corresponding movement decrease or stroke decrease. If the piston moves 5 inches, it displaces 50 cubic inches. Let's get this out of the way. If it moves 5 inches, it displaces 50 cubic inches of air. The first piston was 10 square inches, right? Here's how they calculate it. That was the piston size of the first one on the left. Times 5 inches gives you 50 cubic inches. You got 10 square inches of the piston, 5 inches of travel, and that gives you a volume of 50 cubic inches that it moved, of that much area moved under the cylinder. Then the 50 cubic inches of air was transmitted to the cylinder that was 50 square inches, right? The bigger one was 5 times as big, 50 cubic inches size cylinder. So when you get 50 cubic inches of air in the vessel coming around to a piston that is 50 square inches, then they're dividing. If you take your triangle again, well, no, we're doing distance now. We're doing distance. You got 50 cubic inches of air that's being pushed through the system to piston 2. And then that much air acts on the 50 square inches of area of the piston, causing it to move 1 inch. And the way that works is you take the volume divided by the piston size, and it gives you 1 inch. And so they're taking the 50 cubic inches volume divided by 50 square inches. And 50 over 50 will be 1. And then you end up with 1 inch. It's what you end up with 1 inch. Because when you divide the cubic over the squared, you end up with a number 1, and it's just a plain inch because it ends up being a single inch instead of cubic or square. So that's how they divide that out. They take the volume divided by the area of that second cylinder. And it ends up with a stroke length, a travel of 1 inch. So that's how they can come up with predictably how far something's going to move on paper before they even build the equipment. Yep. just kind of hang with me as we get through this chapter. It'll, again, before you know it, we won't be spending much time in here. It's going to be mostly out there. Yes, that's the way it'll get pretty soon. Because there's chapters in this book that I'm not even going to have to lecture on at all. You'll be able to read them and you'll know it. You know, you'll be fine. So in example 1.7, it shows that for a 5-to-1 pressure increase, there is, or ratio increase, there's a directly opposite travel decrease. The same proportion exists for any leverage ratio. Okay, and then you got air properties that air is lighter, less dense than a liquid, and it will diffuse into another gas, and that water vapor and oil vapor will diffuse into air. Oil particles can be suspended in air. We know that oil does travel from a compressor into air through the pipelines. A little bit of it does. Now, you get into the ideal flow in a pipeline will be streamline or laminar flow, where there's not turbulence in a line. If you got a lot of turns and a lot of changes in pipe sizes and fittings, it creates turbulence in the line. You get air, you get friction in the lines, and you have some losses because of that. So they say when you're designing pneumatic systems, try to avoid changing directions, try to avoid changing sizes of going from one size to another and then changing again, because you're going to lose. You're going to lose air. You know, you're going to lose power whenever you do all that stuff. You'll end up having to boost it to get what you need in the end. And viscosity of air is its resistance to flow. It's a measure of resistance of airflow. And then it's referred to as dynamic viscosity. Bernoulli's law here says that if you go from a certain size of a pipeline, you go to a smaller size through a fitting and through a reducer, and then you go back up. When you go through the reducer like that, your pressure actually goes down because of your surface area of your pipeline in there. If it goes down, your actual PSI in that area goes down. But what happens to the advantage when that goes down is the actual speed of the air speeds up. It speeds up. So if you go small on the size temporarily, well, then it's going to be, the air is going to be moving faster, but yet the pressure goes down. So that's the trade-off there. Well, technically, if you do it with a pressure gauge in there, the PSI goes down, but it's going faster, so you think it's more pressure, but it's not PSI, it's actually speed that goes up. Yeah, your velocity goes up. The velocity goes up. But your actual PSI goes down, you know, if you do that. So that makes sense. We think it's pressure, but it's actually velocity that goes up because it has the appearance of being more pressure. But PSI by gauge, by measurement, it doesn't go up, it goes down, but the speed goes up. The speed goes up. And just as soon as you go back into the bigger area, the pressure goes up and then the speed goes down. The velocity would go back down because it's got to go through a bigger area in the vessel. That makes sense. That's your trade-off there between pressure. Here in a pneumatic system, you have kinetic energy moving, and then potential energy. It's like if it's sitting still, potential energy is energy that's there ready to work, where kinetic is what's in motion. And Bernoulli's law, again, Bernoulli has another law here. If the air velocity or speed increases, the total energy remains constant. The total energy would be your kinetic and your potential added together. If you add them up, both of them at any time, your total energy is supposed to be the same. But it says that if the kinetic energy increases and the total energy remains the same, the potential energy has to be reduced, which would be the pressure. So if your velocity goes up, the pressure goes down. That's your theory there. It goes your basic components of a pneumatic system. You've got the compressor. You've got a storage tank that it stores it in to stabilize your air pressure. There's always a storage tank after compressor. A directional control valve that would switch pressure from the cap end to the rod end to make the piston move back and forth. So that's where you're heading. What your valves out here is being able to control that pressure to get work done to shoot something this way or that way, by way of changing the passages with a spool in a valve to change the passages that the air flows in. So this is where we're heading on a system very soon. Now, when you add more things to it, we're going to add more things to it. Then you have number one. Let me just read while we got the picture up here because you can't see all that at the same time. We're just about done here. And I know it's about time to go too. But it's timing out good. Believe me, there'll be most days you come in here ain't going to be in here. It's going to be right out there doing stuff with your hands. It really will be. So number one is, what is number one over here? Somebody tell me, y'all tell me what's number one. Page 14 in the book. It's a what? And what? Right. So number one would be an intake filter and a silencer. So it's going to be, you know what an oil filter is? Well, the intake filter. Okay. Do you have the intake filter on your vehicle? Absolutely. When's the last time you had it checked? Right. So if you know that, what happens if you go 2 years or 3 years and don't change the intake filter? Then the vehicle starves, right? It's not getting enough air, so it affects the performance of the motor, right? So when you pull it out, what do you see? You get contaminants, right? It's the same thing with air compressor. Could you imagine on the intake stroke, you pull in a certain amount of air and then you shove it through the piston? You got dirty air. What's going to happen? The piston, after a while, you're going to have problems. The seals they're going to be breaking down. Huh? Yeah, they'll rot out. Yeah, and then you'll be pushing contaminants through the system. Then they're going to get into your machine that's got small little valves ticking and talking going on, and you're going to have solenoid valves on the machine clogging up, things like that. It's not good. So here you clean it before you get to what? What's number two? That's the compressor itself. That's going to take it and shove it into a smaller area, going to boost the pressure. Okay. What's number three? Yes. Now, what was I saying a while ago? An aftercooler. Anytime you go up to even a small compressor, you got an intercooler between stages and an aftercooler because it's going to be hot. It's going to can burn you. It's that hot. Okay. Number four. And what does a separator do? Right. When you compress air, think about a certain amount of moisture in the air. But when you compress the air, where there was not droplets in the air, it wasn't raining in the room, was it? It wasn't raining in the room. But when you compress it and get in a small area, then you can develop droplets because you have forced that amount of moisture into a small area. And then you develop. Okay, you get oil in it because there's leakage within the compressor itself, within the mechanical parts of the compressor. You get oil naturally because of the oil in the compressor that it has in it. Some of that seeps through and it gets into the output, and it ends up in the airline just through natural leaks. The compressor leaks a little bit. You know, it's coming from the internal part of the compressor. The oil that's that lubricates the compressor itself actually ends up in the airline. A little bit of it does disperse. And, well, you really want true type of a pneumatic lubricant that's designed for seals to be in the machine. So it's not good to have a lot of that in there. No, you won't have a lot, no way. But there's a certain type of a pneumatic oil that's designed that you put in your little lubricator bowls. If you look, when you come out here on these trainers here, there'll be a bowl on the side of them. You'll see that you put oil in, and then you set a drip rate. And as it runs, there's a little adjustment, a little screwdriver you can adjust. And if you have air flowing through it constantly, blowing through, you can set the drip rate. And there'll be ratings on machines, and they might tell you, you know, 1 drip per minute, 1 drop per minute, 2 or whatever. And you'll set the drip rate whenever the machine's actually chugging and using air. If you overdo it, you'll saturate your lines, and then your mufflers, your discharge mufflers, they'll be pumping oil. So when it's chugging along, I had an operator one time at the plant tell me one time, she got on the intercom and started hollering, "My machine is smoking. Get me a mechanic. I need a mechanic. My machine is smoking." Am I right or not? "I need a mechanic to the lower rotary. My machine is smoking." "I need a mechanic now. My machine is smoking." I go there. I say, "What's wrong?" "Look, my machine is smoking." And it was pumping oil out of the darn mufflers. You got a manifold with air valves, right? And you got a common muffler, 2 mufflers on there, and all the solenoids they breathe out of them mufflers, right? Well, somebody in there had, and it might have been me, whoever, adjusted the oil drip rate and overdid it. You know, here's what happened. I've done it myself. You go to a machine that the oil has been drying for so long that we forgot to put oil in, and it started getting the seals are getting dry. So we go over there and put oil in it. We cut it on, and then we say, "Well, I'm gonna ease up that oil drip rate a little bit and get everything lubricated kind of quick." And then you forget to go back and then turn it down. It saturates the lines, and it starts puffing through the exhaust, and it's an oil mist that comes out, poof, and it's just oil in the air, poof. That girl said, "I need an operator to the lower rotary. My machine is smoking." I said, yeah. But anyhow, so that stuff is etched in my brain. I can't get it out. I can't get it out. I swear. And I see them women at Walmart every now and then. I say, "Oh my God, there she is." You know? Yep. But the separator will get, you got a bowl in there, and that the liquids will fall in the bottom of a bowl, and they'll either drain automatic with a float, or you've got to open a petcock to drain them. So it all depends on if it's automatic or manual drain. And then 7, well, actually, 5. What's 5? It's a pressure switch that senses the pressure, and it's there to start and stop the compressor. If your pressure is below the target, it lets the compressor run, and if it's below the target, it lets the compressor. If it hits the target, it shuts it off. Okay, 6 would be what?
6 is going to be a relief valve.
Right, and 7 itself is going to be what?
Tank.
That's the tank. So on the tank, you got a pressure sensor, and then you have a relief valve. So the relief valve is there just in case if the pressure sensor fails and the compressor keeps going beyond what it's supposed to, and you overpressurize the vessel, you could rupture the vessel and it could split and kill people. So every compressor has to have a watchdog of a relief valve, and it's going to pop off and blow if the compressor overshoots, and sometimes they do overshoot. You know, that they may not regulate right, so it's a possibility for a compressor to overdo it and overpressurize the vessel. It's possible. So that's your watchdog. This is the first one, and this one is a watchdog over the pressure switch if it fails. If it doesn't shut the compressor off when it needs to, that's a mechanical relief valve that has a spring, and it's just going to mechanically pop open and blow off if the pressure switch didn't do its thing. The pressure switch actually tells the compressor to shut off. So this is monitoring in the tank, in the storage tank. And so this is the downstream watchdog basically that says, if this gets over the set point of that sensor that's been set, then it's going to shut this off. It's going to say cut off because the vessel can't take any more, you know, or the process never wants any more than 90 pounds, you know, so you have to shut off. And then after that, I know it's time to go. Let's see. So here you got a 3-stage area that does what? It's a filter. Right. Those three are usually in a package deal that bolts onto the machine. It's called the FRL unit with a filter, regulator, lubricant combo pack, triple pack. So it cleans it again, regulates the pressure to a certain PSI, and then it puts a little drip rate of oil back in it just after it cleans it. So it cleans that oil up, gets it in a target pressure, and then it gives you a little of that clean, nice, clean pneumatic oil that's good for them seals, you know, a little bit, just a little bit. And then here we have what? That's your directional control valve. And it's shown as a manual stick, where you'll run a manual stick on some, and then some are going to be solenoid operated. And then some valves are actually pilot operated. We can get some other equipment out of the room that's a little more involved than this. It's got pilot valves you can have an air valve running another valve. And then you've got your what here? Right, you have a cylinder here, and then sometimes, you know, you've got air motors. You got rotary things that run, and sometimes there's rotary actuators that run in a swing arm. You remember how we looked back here in the automation system, and it had some of the things out there came around like this. It would grip, it'd come around 180 degrees and then go down and drop. That's a rotary actuator, that's air. And so you got the rotary stuff going on for pick and place, and you've got the motors, the air motors, and you've got even the grippers, this air, and the vacuum tools, and you got a lot of stuff going on back there in that system that's air. So anyway, so that's enough. It's time to go. That was some very good timing. That was good timing that we finished that chapter. So if you haven't done the worksheet, try to knock out the worksheet over the weekend. You got, you know, it's 3-day weekend. Of course, if you're working on it, you don't. Yeah. What do y'all do like on you don't do anything on Martin Luther King? You don't get that off, do you?
Well, they got a big project going on.
Project.
So, but I'm gonna work Saturday, Sunday, and be off Monday.
You're gonna be off Monday. Once you sleep in, get some rest. If you
That worksheet online?
it is. It's in Moodle. Yep. Y'all show you. It's I'm gonna do I have everything in Moodle this semester. It's gonna be automatic grading. So as soon as you finish them, there's your worksheet right there.
I got it.
Yes.
I had even looked on there past doing that one thing.
You got 21 questions. All of them are multiple choice.
I want to do it over. I need to do it over.
What you do? You didn't do too good.
Yeah, I'll be around this weekend.
Y'all have a nice. Have a nice. Hope you don't. Hope you're gonna get Monday also. That's good.
Yeah, I chose Monday. They told me to work what?
We gonna get
Saturday. I gotta work 2 days. They told me to come in Saturday.
You let us do it.
Work Monday. I'd rather come in Saturday and Sunday, get double.
Make more money. Make more money. That makes more sense. That's smart. That's why you make the good book. You got smart.
That's why I'm going to play tennis.
Hey, that sounds good. That sounds good. Thank you, man. Thank you. God bless you, man.
Yes, sir. I'll
Hey.
see you Tuesday.
Joe, yeah, this fellow right here, he went to my mom's funeral, man. Went to the wake and went to the funeral. Sure did. This dude, he's sticking with me, man, like a brother. I ain't kidding. Yeah, him and McGill and Wilbur Vasquez. Yeah, sure did. Yep.
I seen you yesterday. I was coming home. I drove by. You were at Bojangles.
Yeah. I was sitting out there, but I love that tea, man. I'm hooked on the tea, man.
Yeah,
I can't eat the spicy chicken, but I can eat the grill. But that tea, I gotta have it, man.
I see your truck like I know you.
I'm out there on that phone, or I'm texting or doing something or other, or I might be taking, man, you might see my head right there. I'll be out, man.
All right, bro. Will you
Have a
night?
good weekend, man. God bless you, man. Thank you. Good guy, man. He worked hard, man. He sure does. He got his welding degree, and he come over here. We got a job at Smithfield, got in welding. Now he's.
Is there? Hey, bro, you think is there any way I can make my a grinder to cut my lock? That's my lock.
Is,
Yeah, I just don't know where my keys are. I don't know.
yeah, you can do that. Yeah, sure.
All right. Have a good night.
You too, thank you. How's your boy doing? See,
They doing good.
how old is he now? About 3,
Or
4. Oh, got a picture? Yeah.
yeah.
Okay, I'm shutting this session off here. Let me cut the recording off.